The question is, how do you design systems specifically to be flexible, and how do you know where the flexibility in the system should be? We've developed in the research a method called time-expanded decision networks. It's a method that allows you to model your system and the different configurations of your system that you might adopt, and it allows you to also model future scenarios. You then play these different future configurations of your system against the future scenarios, and hypothetically or through simulation try to assess how would the system perform under different future scenarios. And for each of these future scenarios, you assess both the performance of the system, the operating cost, the failure modes of the system, and it helps you figure out which future paths are more favorable, which ones might be dead ends and are not worth investing in. And it has proven to be a very effective method. We've applied it to the design of future launch vehicles. We're currently applying it to the next generation of automobiles. And it helps you understand, in some sense, the hotspots. Where are the hotspots in your system that are likely to be the subject of change? Which parts of your system are invariant? Which parts of your system are, in a sense, shielded from future changes, and you can therefore have more confidence or freeze their configuration. And so a lot of it is about managing the design process differently, being more strategic about the choices you make with respect to selecting the right technologies, building in design margins, and in a sense you could say future-proofing your system designs. One of the specific projects that we worked on to build in flexibility and figure out where to build in flexibility for the future of the system is an automotive platform design. This project was carried out with one of the large US automotive manufacturers. We worked with them very collaboratively in terms of analyzing the current state of the system. This particular project, the challenge was to design a vehicle platform that could support medium and large-scale sedans, so be scalable over a large range of sizes and performance tiers for vehicles, while still being economical to manufacture and satisfy all the crashworthiness and regulatory constraints. So when we analyzed the future market demand for the types of vehicles that would be derived from this platform, we found some of the key uncertain variables. For example, and this is very non-intuitive at first, the demographic evolution of our population. So we know that we have an older population, we have older drivers, and one of the things they really care about is what's called ingress-egress, the ease of getting in and out of the vehicle. You can quantify the ease of ingress-egress into the vehicle, and it depends on some key variables like the overall width of the vehicle, the floor to hip point height. There's some key dimensions in the vehicle that drive that particular metric. So now if you think about how that population will evolve, you can project that onto the key dimensions, the key design variables, the key material choices in the vehicle, and then understand, well, given this evolution, what are the things that we will have to modify, which things are pretty much stable and invariant over 5, 10, 15, 20 years. And based on that, we were able to make very specific design recommendations to design this vehicle platform to satisfy the immediate next generation, but also the second and third generation after that. The need to design for flexibility and evolvability of systems is greater today than it has ever been, but the opportunities are also greater than they've ever been. The need is greater because of globalization. Many firms that we talk to, many system designers, are no longer operating only at a local and regional scale. Nowadays, even as a small and mid-sized firm, you will deal with different countries, with the emerging countries, China, India, Brazil, Russia, the BRIC countries. You will sell your products and operate your systems in the more established countries in Western Europe and North America. And the demographics, the change in in the population, the growth in the population, the aspiration of these of people in these countries, and the opportunities are enormous. This is conflated with relatively large volatility in the financial markets, with uncertainties about the availability of key resources. If you look at the prices, for example, for key inputs into systems and manufacturing like copper, steel, aluminum, a lot of the key resources, their prices have fluctuated dramatically over the last decade, more than previously. And so the conflation of all of these major factors really makes it necessary to think about flexibility and not design for a fixed future that you're assuming. It has made that problem much more urgent than it's ever been. On the positive side, we have a lot of new capabilities that are coming out of the research, that are coming out of really an understanding that we have data that's available. We can do modeling, simulation, and visualization of these systems at an unprecedented scale and level of detail. And we also have technologies that enable us to be more nimble, more flexible in adapting to future circumstances.